if I interpret this as the single digit, 0.0, 0.1, probability of being less than 0.0 is 0. Probability of being between 0.0 and 0.1, in other words, the probability that the leading fractional digit is 0 is 0.3. The probability that the leading fractional digit is 1 is 1. So basically, excuse me, my number line exists here. So half the numbers exist here, half the numbers exist here. And then what I'm arguing is that I can bifurcate. So in other words, given that the number is between 0 and 1, half of the number line exists with 0.00 as the leading digits, and half of it exists with 0.01 as the leading digits. So I can apply the split again to get that. And now over here, half the numbers have, or half of these numbers have 0.10, and half have 0.11. So again, I can apply the split up here. And so on. So the idea is that I can recursively split these now into 3 digits, 0.000, 0.001, 010, 0.011, and so on. So I can split those. I can split here. I can split here. And I can split here. Now, the lengths of these intervals are all the same, and each of these intervals has a corresponding vertical interval, which are not the same. So that's the key idea. The key idea here is that is two things. Firstly, from this I can directly calculate what the f bars are. If I know what these intervals are, then I can directly calculate f bar. Secondly, as I'm about to show you, when I have an IID source like this, I can calculate fx easily without necessarily knowing what for a particular x, without necessarily knowing what the value of the function is for any other x. So what I can do is I can directly calculate where this interval is. I can then calculate the halfway point. I can then convert that to a binary representation, and then because I know the length of this interval, I know how many digits I should use, and then I can directly get my code word. So it's an easy way, it's a relatively low complexity way to encode, and because it's a Shannon-Fano Elias code, we're guaranteed that it's a prefix code, which is good. So let's just look as an example at the first step of this bifurcation. What I really need to know, so here's the sequence of things I need to know. I need to know f of x, or actually let me use better notation than this. So I have random variables x1, x2, x3, and so on. So what I need to know, in my first example, I'm going to extend my source from x1 to x2. I already know fx, fx1. So from that, I need to know fx1, x2. Once I know that, I need to get f bar, x1, x2. Excuse me. We don't necessarily get this from fx. What we get it from is p of x, p of xi. Once I know that, I need to get f bar. F bar is what I encode, so then I just need to figure out the length, L of x. And given these two, I can directly obtain my code word. So, how does this bifurcation work? Well, here's my number line from point 0, point 1. So half, again, half of my numbers will have a leading digit of 0, and half will have a leading digit of 1. My f of x looks like this. Where this, the length of this interval is p0, and the length of this interval is p1. And this here is f0. Now, if I want to get f x1, x2, so remember the interpretation is that there's a decimal point right there. This is equal to the probability that point x1, x2 is less than or equal to some specific decimal expansion x1, x2. So what this should be equal to is, okay, if, well, let's think of some specific examples. So if, just to get ourselves warmed up, if, let's say x1, x2, these values is 0.11, or actually 0.10, that's a good example. So the probability that this random variable is less than or equal to 0.10, well, for one thing, if the leading digit is 0, in other words, if the leading digit is less than 1, then we're guaranteed that this will be less than 0.10. In other words, if x1 is less than 1, then we are guaranteed that these digits will be less than 0. So, in order for these to be less than that, we have to have that this is less than that, or this is equal to that, and this is less than that. So, this is less than that, that's probability x1 is less than 1, or probability that x1 is equal to 1, and x2 is less than or equal to 0. Let's think of
I'm sorry.
Yes.
Less than or equal to 0 means starting with double zeros.
That's just looking at this individual digit right here. x2 is the second digit. So, think of all of the possible sequences x1, x2 that are less than or equal to 0.10. So, the number of such sequences is 0.00, 0.01, and 0.10. So, if the first digit is less than, if the first digit is less than 1.
You included that, yes.
Yes. And so that's this term right here. If the first digit is equal to 1, it's still possible that, that this expansion is less than or equal to 0.10, as long as the second digit is less than or equal to 0.
Isn't there only one possibility that it's equal? How can the second digit be less than 0?
It can't, actually, so that's a good point. I'm just trying to build up a general case from examples.